Okay, so hello everybody, and welcome to the first lecture of Physics 47 for this semester. Today what we're going to be doing is tackling a basic thermal physics review. So we're going to go over some of the concepts that you're going to need to know going into Physics 47. And we'll spend the first week of class or so on this review of basic thermal physics. The relevant textbook reading is given on the slide below the title, so do review those sections from the textbook. That's what we'll be talking about during this review. And before we launch into the lecture, I want to talk a little bit about how you should approach these lecture videos. The first thing I'll say is you should have a notebook with you and take notes as you go through the video, just like you would if you were in a face-to-face class. But that said, the lecture slides that I'm going to be using here are going to be available on Canvas. So don't feel the need to copy down every single word and picture from the slides. Instead, what I'll be doing is expanding on some of the things that are shown on the slides. I might be doing derivations, I might be doing example problems and things like that. That's when you should really focus on taking notes. Again, you don't necessarily need to copy everything that's on the slides because that will be available on Canvas. So with that said, let's launch into our review of basic thermal physics. And the first concept that we're going to tackle here is conservation of energy. So I'd like to begin this discussion with a quote, and here it is. There is a fact, or if you wish, a law governing all natural phenomena that are known to date. There is no known exception to this law. It is exact as far as we know. The law is called conservation of energy. It states that there is a certain quantity, which we call energy, that does not change in the manifold changes which nature undergoes. That is a most abstract idea because it is a mathematical principle. It says that there is a numerical quantity which does not change when something happens. It is not a description of a mechanism or anything concrete. It's just a strange fact that we can calculate some number, and when we finish watching nature go through her tricks and calculate the number again, it is the same. Okay, so this is a quote by the famous physicist Richard Feynman, and I think it does a really good job of getting at the heart of conservation of energy as a concept. Because energy is not really a substance. It's not anything material that you can hold in your hand. Really, the way to think about energy is it's something you can calculate, okay? And we have different formulas for calculating different types of energy. And if you're very, very careful in how you keep track of the different types of energy that a system can have, you're going to find that it's conserved, right? So even if some really complicated process is happening, you calculate the total energy, you're always going to find that it stays the same. That's the idea. So again, the takeaway point is, energy is something you can calculate. It's not really something concrete that you can hold in your hand. So with that said, let's get into how we go about applying the idea of conservation of energy. So the first thing we want to talk about is a distinction between a system and its environment. Okay, so when we talk about a system in physics, we're just talking about the collection of objects that you're choosing to analyze. So you choose what the system is. You say, I'm going to focus on the motion of these objects, and that's your system. Okay? And then as soon as you've chosen your system, the environment is just everything else. Anything outside of your system is the environment. So again, it bears repeating that the system is something you choose to define. It's just whatever you're choosing to focus on in your analysis. The environment is just everything else, anything outside your system. Well, if you think about the system and the environment together, that's everything, right? So together, the system plus the environment is the universe. That's everything you could possibly have. So what is conservation of energy really telling us then? Well, the law of conservation of energy says that it's the total energy of the universe that doesn't change over time. Okay? So energy could be flowing in or out of your system or in or out of the environment, but if we really consider everything, the entire universe, energy is going to be conserved. That's the idea. Okay, So if we really want to be able to use conservation of energy to make a calculation or predict how a certain system is going to behave, we need to talk about the different forms of energy that a system can have. So let's clarify some terms here. Let's start with kinetic energy. Okay, we say that a system has kinetic energy because of the motion of macroscopic objects within the system. So a really simple example is if I were to pick up a baseball and throw it across the room, we would say it has kinetic energy by the way it's moving. If it's moving faster, it has more kinetic energy. If it's moving slower, it has less. And if we look at the formula, and this is a formula you should be familiar with, K is equal to 1/2 mv squared, we see that the kinetic energy depends on the speed. That's V in the formula, the speed of the object. So kinetic energy is energy of motion. On the other hand, if we look at potential energy is something a system has because of the location of objects within the system. So to make this a little bit more concrete, remember the formula for gravitational potential energy. This is something that you should have seen back in Physics 45. U is equal to mgy. So U is the variable that we use for potential energy, and Y in this formula represents height. So how high off the ground is a particular object. So if we go back to the example of the baseball, if I throw it across the room, the higher the baseball is above the ground, the more potential energy it has. And the lower it is, the less potential energy it has. But in general, what we say is potential energy depends on location, depends on where things are positioned in your system. Okay, the next thing is internal energy. So if we want to understand what internal energy is, we have to understand that it has to do with microscopic motions of the atoms and the molecules that make up the system. So to give you an example to look at, let's consider just a box of gas. And that box of gas is just resting on a table, okay? So as far as kinetic energy is concerned, the box itself is not moving around, so there's no macroscopic motion going on. We would say K, the kinetic energy, is equal to 0. And in a similar way, you could set the potential energy equal to 0. You're free to set the 0 point for potential energy wherever you like. So the point is there's no macroscopic motion happening that you can notice just by looking at the box. But if you were to zoom in and look at the box of gas on a microscopic level, you'd see that there's actually a whole lot of motion going on, right? The gas consists of a bunch of molecules that are in constant and random motion. So to show you what this looks like, I'm going to play an animation of a box of gas molecules, and we can kind of see what's going on here. So in reality, there will be many, many more molecules than I'm showing you here, but you get the idea of what's going on. The molecules are constantly bumping into each other. They're constantly bumping into the walls of the container, and it looks like a big chaotic mess. But there is some microscopic motion going on there, and that's where the internal energy of the gas comes from. Okay, it's energy you only see by looking at the system on the microscopic level and looking at the motions of those atoms and molecules that make up the gas. By the way, if you want to see this animation on your own time, you can click the link at the bottom of the slide. So a couple more terms that we need to really clarify and get straight in our heads. Let's talk about heat and work. So the big picture here is don't think about heat and work as forms of energy that a system can have. So it makes no sense, for example, to say that, my system has 100 joules of heat or it has 100 joules of work. Those are kind of nonsensical statements because heat and work are ways that energy can be transferred from a system to its environment. It's not energy the system has, it's a transfer of energy that a system undergoes. So to give you an example, or actually to define these words, let's start with heat. So heat is given by the variable uppercase Q. And when we talk about heat, we're talking about a transfer of energy due to a temperature difference between the system and its environment. So to give you a concrete example of this, let's say the system is a pot of water, and then let's say the environment is very hot. Maybe we're lighting a flame under the pot. So we know what's going to happen, right? We know that there's going to be energy transferred from the environment to the system. And that transfer of energy is called heat. But again, it's not energy the system has, it's the transfer of energy that we're talking about when we talk about heat. So in a similar way, we can talk about work. Work is given by the variable W, and it's a transfer of energy due to a force acting over a distance. Okay, so the formula that we use to define work is the dot product of F, which is the force, and dr, which is a little tiny displacement. And if you integrate that, you get the work. So again, to illustrate this with an example, let's say the system is a block or some really big block that you want to push across the floor. And the environment will be some person that's pushing the block, right? So the environment is exerting a force on the system, right? That's the push. And in doing so, the environment is doing work on the system, right? And that is a transfer of energy from the environment to the system, because what's the effect of pushing the block? You're going to make it move. You're going to increase its kinetic energy, okay? So those are just two ways, basically, that you can transfer energy, heat and work. That's what you want to think about. Okay, so with all of those definitions in mind, okay, we've got kinetic energy, we have potential energy, we have internal energy, and then we have heat and work. Now, with all those definitions in mind, we can really get to the heart of conservation of energy and how to write it out as an equation. So here's the equation. Delta K plus delta U plus delta E internal is equal to W external plus Q. And if we kind of break this down, on the left-hand side of the equation, these are just different ways the energy of a system can change, right? The kinetic energy can change, the potential energy can change, and the internal energy can change. Okay, so on the right-hand side, we have different ways that energy can flow in or out of the system, which is, again, work or heat. And the statement that's being made in this equation is, if the energy of the system changes, that's the left-hand side, then some energy must have flowed in or out of the system. That's the right-hand side, right? Because overall, energy is conserved. So conservation of energy applies to the universe as a whole, right? The total amount of energy in the universe is conserved. So that means if a system gains some energy, okay, if the energy of a system increases, it must have taken in energy from its environment. And then if a system loses energy, it must have given off some energy to its environment. So regardless of what's happening, the total amount of energy in the universe is conserved. That's the idea kind of underlying this equation. Okay, so a little bit more about that conservation of energy equation, just to make this a little bit more concrete. I want to make an analogy. So the analogy is a piggy bank with some coins in it. And what we're going to assume is coins in the world aren't created or destroyed. Okay, so the total number of coins in the world is not going to change. So this little box here is your piggy bank, and there's some money in there. Of course, the money in your piggy bank can change. There's nothing wrong with that. But the only way it can change is if you put coins in or if you take coins out. So putting coins in, that's making a deposit. And then taking coins out, that's a withdrawal. How do you spell withdrawal? Okay, there we go. Sorry, I can't spell, guys. So let's call that, positive if you make a deposit and negative if you make a withdrawal. So we can write down an equation, like a conservation of coins, let's say, equation. And that says delta, money in the bank. So if there's a change in the amount of money in your piggy bank, right? That must equal deposits minus withdrawals. Okay? So the change in the amount of money in the bank is just how many coins you put in minus the amount of coins you took out, right? That's easy to understand because, of course, the total number of coins doesn't change. Well, that's really the same idea behind our conservation of energy equation. Okay? Because basically we have delta K plus delta U plus delta E internal. These are just changes in the total energy that your system has. Okay? On the other side, we have work and heat, which are just different ways that energy can move in or out of your system. So it's really the same idea as this analogy that I made. Okay, so now we're on the first question for the class slide of the semester. So normally in an in-person class, what I would do is kind of pause the lecture and then give the class maybe 5 minutes or so to work on this question. And I'd walk around the room and help students out solving this problem. What we're gonna have to do in this case is I'm gonna ask you to pause the video, try to work on this question, and then when you think you have an answer, come back to the video, and then we'll see if you got the question right. Anyway, here's the question. If you drop a ball from a height of 15 meters above the ground, what will its speed be just before hitting the ground in units of meters per second? Neglect air resistance and use conservation of energy to calculate your answer. Okay, so a couple relevant equations for kinetic and potential energy are given at the bottom. So give this a shot and let's see what you get. Okay, so the first thing in any sort of conservation of energy problem that you want to do is define what your system is. So for the purposes of solving this problem, I'm going to define the system to be the ball plus the earth. And I'll explain why I did that in a second. But let's draw a picture of our system. So we're going to keep track of the height, y, using this y-axis. And I'm just going to set the ground to be y equals 0. So that means the starting height is 15 meters. And there's the ball at the starting height. Now the ball starts at rest. So the ball starts at rest, meaning its initial speed is going to be 0. So then in this initial state, it's dropped and it falls to the ground. And we want to know how fast it's moving down just before it hits the ground. So that's V final. So I'm going to start with the big conservation of energy equation. Delta K plus delta U plus delta E internal is equal to work plus heat, W plus Q. So let's ask the question of our system, is there any change in internal energy going on? Well, no, we don't have to worry about that. Is there any work done by some kind of external force acting on our system? Well, no, because we've accounted for gravity by including the Earth in our system, so there's no outside force doing work. What about heat? Well, there's no heat flow in this problem that we have to worry about. So actually, this reduces to delta K plus delta U is equal to 0. Okay, so what's delta K? Well, that's going to be 1/2 mv final squared, that's the final kinetic energy, minus 1/2 mv initial squared, that's the initial. What's delta U going to be? Well, that's mg y final minus mg y initial. And that all equals 0. That's our conservation of energy equation. All right, well, there are a few things we can simplify. V initial is 0, so I can cancel out that term. And then y final is also 0 because it reaches the ground. So we have something really simple now, which is 1/2 mv final squared is equal to mg y initial. We don't even need to know the mass, that drops out. So therefore v final squared is equal to 2g y initial. And then if I just take the square root of both sides, v final is the square root of 2, and let's put the numbers in. G is 9.8 meters per second squared. Y initial is 15 meters. So if you crunch those numbers, what you're going to get is about 17 meters per second. So that's how fast the ball is moving just before it hits the ground if it's dropped from that height. Of course, we're ignoring air resistance in this. Okay, so that was a pretty simple example. Let's do a more complicated one next. Okay, so here's another example that I want to show you guys for conservation of energy. Let's say we have a block of mass 2.5 kilograms that's dropped from a height of 1.5 meters onto a spring that has a force constant, K, of 474 newtons per meter. At the moment that the spring brings the block to a stop, how much is it compressed from its equilibrium length? Okay, so a couple different formulas that are relevant here. Kinetic energy, as always, 1/2 mv squared. And in this case, we have two types of potential energy to think about. We have gravitational, which is mgy, but we also have a spring potential energy, which is given by 1/2 kx squared. So hopefully this all looks familiar from Physics 45. Let's work this one out using conservation of energy. All right, so let's work this one out. We're going to start as usual by defining what the system is. And again, you're free to do this any way you like, but for our purposes, let's say the system is the spring, the block, and the earth, okay? So let's take a look at the initial state of our system when the motion starts. So what we have is the block hanging above the spring, and it's initially at rest because it's dropped. So it's not given any initial speed. Its initial speed is 0. Okay, then what happens is this thing falls downwards onto the spring, and then it hits the spring, and then it compresses the spring a little bit. So in the final state, the spring has brought this block to a stop, so it has 0 final speed as well, and that's what we're dealing with, okay? So one thing we need to do is keep track of the positions of different things in the system. In particular, I'm talking about the block and the spring. So to do that, I'm going to draw the y-axis like this. There's y. And I'm free to put the 0 point. I'm free to define y equals 0 wherever I like. So I'm going to do it right here, where the spring is initially in the initial state. And what are we told? That the block starts 1.5 meters above the spring. So that's going to be y equals 1.5 meters right there. Let me draw that a little better, 1.5 meters. And then what we want to know is how far does the spring get compressed in the final state? So I actually don't know what that is. Let's call this y final. Let's leave that as an unknown variable. And that's the whole point of the problem, is to find y final. Okay? So that sets it up for you. And then we'll write down our conservation of energy equation, delta K plus delta U plus delta E internal is equal to work by outside forces and Q, heat. So the situation is actually very similar to the last problem. There isn't any internal energy change that's relevant in this problem. There isn't any outside force doing work on the system because we've included the earth and the spring in our system. And there's no heat that we need to worry about either. So actually, this is just delta K plus delta U is equal to 0. But we do have to be a little bit careful about that because there's only one type of kinetic energy. The block is moving around. But there are two types of potential. There's gravitational potential energy, and there's also the spring potential energy. So we have to include both of those, and then we can set the right-hand side equal to 0. Okay, so let's write this all down. Well, actually, first, before we get to the next step, let's say what we know about delta K. So there's initially no kinetic energy, right? Because the block starts off at rest. And in the final state, there's also no kinetic energy. So the change, the delta K, is 0. So you can cross that out before we do the next step. All right, so now let's write down our equation. We have delta UG, so the change in gravitational potential energy. That's going to be mg y final minus mg y initial. What about for spring potential energy? Well, what I'm going to have in this case is 1/2 K. And remember, for spring potential energy, it depends on how much the spring is being compressed. So it's being compressed by an amount y final shown in the diagram. And we square that. And then I subtract the initial spring potential energy. But guess what? That's 0 because the spring starts off not compressed at all. Okay, and then that is all equal to 0. So that's our conservation of energy equation. So at this point, what I'm going to do is plug in everything we know. So I have 1/2 K y final squared. Well, we're given that K is equal to 474 newtons per meter. And then I have y final squared because I don't know that, it's still an unknown variable. Okay, I also have mg y final. So I have plus, the mass we were given is 2.5 kilograms, g is 9.8 meters per second squared, and then we have y final. Okay, and then lastly we have minus mg y initial. So m is 2.5 kilograms, g is 9.8 meters per second squared, just like before, and then y initial is 1.5 meters. Okay, 1.5 meters, and that all equals 0, like this. So what kind of equation is this? We're trying to find y final, which tells us how much the spring is compressed, but this is a quadratic expression, right? We have a y final squared, we have y final, and then we have a constant term. So to simplify the expression a little bit, 1/2 of 474 is 237. And then the second term, the constant out front is 24.5. And then the last term is 36.75. Okay, so that's just the quadratic expression where the coefficients a, b, and c in the quadratic formula are shown right there. So y final, we use the quadratic formula. If you remember, it's minus b plus or minus the square root of b squared minus 4ac over 2a. And again, you know what to plug in for a, b, and c. So you get these two possible answers. I'm just going to jump to the results you get from doing that calculation, which are 0.345 meters or negative 0.449 meters. Those are the two answers we get from the quadratic formula. How do we know which one is right? Well, y final should be negative, right? It's below 0. So we know to choose the negative solution. And this is telling us the spring is compressed by 0.449 meters, or we could say 44.9 centimeters. So that's how you do that one. All right, so next, let's talk about temperature and thermal equilibrium. These are two concepts that I want people to have straight in their heads before we move on to the next part. So let's talk a little bit about these things. And we'll start with temperature. So what I want to get across here is what is a good physics definition of temperature, okay? So we know intuitively what temperature is, right? We know that if you touch something and it feels cold, it tends to have low temperature, and if it feels hot, it tends to have a high temperature, but that's really about your perception of temperature, right? That's your sensation of temperature. What we want to do is define temperature in physics terms, in terms of what's happening with the atoms and the molecules that make up the object. That's what we want to achieve right here. So we're not going to flesh out the full picture right now. We're going to come back to this issue later in the next lecture, but I want to give you some kind of sense as to what's going on. So the long story short is what we perceive as hotness or coldness of an object is a direct result of the random motions of the atoms and the molecules that make up the object. So a result that we're going to derive later on in the next lecture is that the average kinetic energy of the molecules that make up an object is directly proportional to its temperature. We're actually going to derive that in the next lecture. So what you should have in your mind conceptually is, the faster the atoms and the molecules are moving on average, the higher the temperature is. And then the slower they're moving, the lower the temperature is. So to give you a picture of this, take a look at the animation on the bottom right of the slide. This is an animation of what it might look like if you were to zoom in and look at a liquid on an atomic level. You would see a bunch of randomly moving atoms and molecules bumping into each other, sort of like this. And the motion is very chaotic and hard to keep track of. But you could say, on average, how much kinetic energy do those molecules have? And when you do that, you'd be making a statement about the temperature, right? Because the more kinetic energy and the faster moving those molecules are, the higher the temperature, okay? And that takes us to the idea of absolute zero. So if you go the other way and imagine slowing down these random motions and making them less and less energetic as time goes on, there's only so far you could go in that direction, right? Because at some point, if you slow things down enough, motion stops altogether, right? You can imagine cooling something off to the point where the atoms and the molecules that make it up just completely stop moving altogether. And that's what we call absolute zero. So absolute zero is the lowest physically possible temperature. And what you should be thinking about happening when an object reaches absolute zero is that the motions of the molecules stop altogether. So I don't want to get into too much detail about this, but it turns out that absolute zero is not a temperature you can actually reach, but you can get pretty close to it. Okay, and again, what you should have in mind is molecular motions stopping altogether at absolute zero. Okay, so now you have some sense of what temperature is in physics terms. Now let's get on to something a little bit more practical, which is how do we measure it? What are the different temperature scales that we need to know? So there are three. One of them is Fahrenheit, the other is Celsius, and the other is Kelvin. These are temperature scales that you should be familiar with. So we'll start with the Fahrenheit scale, which is most commonly used in the US to report the weather. The freezing point of water in the Fahrenheit scale is at 32 degrees, and then the boiling point of water is at 212 degrees. And in between those two temperatures, you have 180 degrees Fahrenheit. Okay, that's how the Fahrenheit scale is defined. In the Celsius scale, the freezing point of water is set to 0 degrees. The boiling point is set to 100 degrees, so you have 100 degrees in between those two temperatures. In the Kelvin scale, the increments are the same as in the Celsius scale, but instead of setting 0 to be the freezing point of water, 0 in the Kelvin scale is actually absolute zero. So a really important difference between the Kelvin scale and the other two is that you can have negative temperatures in Celsius, right? It's possible to have something be colder than the freezing point of water. But in the Kelvin scale, that's not possible, okay? When you have 0 in the Kelvin scale, that is absolutely as low as you can go in terms of temperature, because again, it's absolute zero. Okay, so one thing we need to know is how to convert between these different scales. And there are two formulas that I'm putting on the slide here. The first one tells you how to convert between Celsius and Fahrenheit. So this says that the temperature in Fahrenheit is equal to 9/5 times the temperature in Celsius plus 32. Okay, the next formula says if we want to convert between Kelvin and Celsius, you take, if you want the temperature in Celsius, you take the temperature in Kelvin and subtract 273. Okay, so I want to talk a little bit about where those formulas for converting between temperature scales come from. So let's start with a couple facts. The freezing point of water, of H2O, if we're using the Fahrenheit scale, that would be at 32 degrees. But if we were using the Celsius scale, that would be at 0 degrees. Okay, so it's, in other words, it's 32 degrees higher in the Fahrenheit scale. So we have to add 32 degrees to whatever we have in Celsius to get Fahrenheit, okay? Okay, the next fact that we're gonna write down is that there are 180 degrees Fahrenheit between H2O freezing point and boiling point. But if we're using the Celsius scale, we would have only 100 degrees Celsius between those two. So the ratio, here we can take a ratio, 180 degrees Fahrenheit is equivalent to 100 degrees Celsius. And as a reduced fraction, that's 9/5. So that's where the conversion comes from. The temperature in Fahrenheit, first we have to take 9/5 times the temperature in Celsius, because again, the increments are different. But then we have to add 32 because one scale is offset from the other by 32 degrees. So that's where this comes from. Okay, so let's do a couple examples involving temperature scales. So the first one is this. Normal human body temperature is 98.6 degrees Fahrenheit. What is this temperature on the Celsius scale and on the Kelvin scale? Okay, the other question is, at what temperature do the Celsius and Fahrenheit scales have the same numerical value? So again, pause the video for a second and see if you can work these out, and then we'll get to the solution. Okay, so there are two questions here. The first one is about normal human body temperature. And we want to convert that from Fahrenheit to Celsius. So we know from what we just did earlier that the temperature in Fahrenheit is equal to 9/5 times the temperature in Celsius plus 32 degrees. Okay, so we actually want to turn this around and solve for the temperature in Celsius. So the first thing we'd have to do is take the temperature in Fahrenheit minus 32, and then we'd have to multiply that by 5/9. Okay, so what we have is 5/9. The temperature in Fahrenheit is 98.6, subtract 32, and what we get is 37.0 degrees Celsius. Okay, now we can also solve for this in the Kelvin scale, because we know that the temperature in Kelvin is just the temperature in Celsius plus 273. Okay, so just add 273 to what we just calculated there, and you will get 310 Kelvin. Okay, so that's normal human body temperature in those other two temperature scales. Okay, the second question had to do with at what numerical value, okay, do we get the same temperature in degrees Fahrenheit or degrees Celsius? Okay, so here's how I'm going to go about doing this. I'm going to let X equal the temperature in degrees Fahrenheit, but the assumption is it's the same temperature in degrees Celsius because there's some point where those two scales line up with each other. And all I need to do is take the formula for converting between the two scales. So temperature in degrees Fahrenheit is equal to 9/5 times the temperature in degrees Celsius plus 32. And then just replace those with X. Okay, so here, X is equal to 9/5 times X plus 32. Okay, so subtract 9/5 X from both sides. So I'll have X 1 minus 9/5 on the left side. And on the right side, I'll have 32. And if you reduce what's in the parentheses, it comes out to minus 4/5 times X equals 32, or X is equal to minus 5 times 32 over 4. What does that work out to? Well, that's minus 40. So in other words, minus 40 degrees Celsius is the same as minus 40 degrees Fahrenheit. That's the only temperature where the two scales give you the same numerical value. So the next topic here is thermal equilibrium. And this is a bit of a tricky concept to fully grasp, and we're going to develop it over the next month or so. And it's not until we actually reach the end of chapter 20 that we'll fully understand thermal equilibrium and why it happens the way it does. But for now, let's just state what thermal equilibrium is, and we'll do that with an example. So let's consider two blocks that have two different temperatures. So if you look at the bottom of the slide, you see there's a red block, which starts off at 300 degrees Celsius. And then there's a blue block that's at 0 degrees Celsius. So we know intuitively what happens if we put the blocks in contact, we make them touch. We know that the hot object is going to decrease in temperature, it's going to cool off. And then the cold block is going to increase in temperature, okay? And this is going to happen until the point where the two blocks reach the same temperature. So there are a lot of different ways this could happen, depending on, the size of each block and what each block is made out of. But one possibility is that the final temperature that they both reach is 150 degrees Celsius. So we'll use that in our example. So that final state that the blocks reach once they are at the same temperature is called thermal equilibrium. We say they're in thermal equilibrium once they reach the same temperature. They're not in thermal equilibrium before that. So if we look at what's happening to this system before thermal equilibrium is reached, we know that heat must be flowing from the hot block to the cold block before they reach the same temperature. So in other words, we say that there's a Q shown with a little arrow going from the hot block to the cold block. And then once thermal equilibrium is reached, that heat stops flowing altogether, and then they're at the same temperature. So that's the basic idea behind thermal equilibrium. Again, to recap, you have two objects with different temperatures. Okay, they're not in equilibrium. Heat flows from the hot one to the cold one, and this happens for a while until they reach the same temperature. Once they reach the same temperature, we call that thermal equilibrium. We call that final state thermal equilibrium. Okay, so we want to understand a little bit, why does that happen? Why is it that heat flows from hot to cold and not the other way? And then eventually heat stops flowing and you reach equilibrium. Well, if we think about what's happening when you put a hot object in contact with a cold object, remember that the atoms and molecules that make up each object are jiggling around. They're randomly moving around. And so when you put the two objects in contact, those randomly moving atoms and molecules are colliding with each other. They're bumping into each other. And when atoms or molecules bump into each other, they exchange energy. In other words, you can exchange energy from one to the other. So what's happening is the hot object is losing energy through these collisions of atoms, and the cold object is gaining energy. But this only happens for so long, because at some point, you're going to reach a point where the molecules have the same energy on average. In other words, they reach the same average kinetic energy. And at this point, we say that the two objects have the same temperature, and that's the definition of them being in thermal equilibrium. Okay, so let's really think about this a little bit more clearly. When the system starts off, and you have a hot object and a cold object, energy is more concentrated in the hotter object, right? It has more energy on average than the colder object does, okay, if we look at it on a sort of atomic level. But then, as time goes on and you let them exchange energy, okay, the energy goes from being concentrated in the hotter object to being evenly spread out. Once you have thermal equilibrium, that's really what's happening, is the energy goes from concentrated to evenly spread out throughout the system, okay? Okay, so let's take a look at a couple examples of a system that reaches thermal equilibrium, and let's see if we can understand conceptually what's going on in each case. So let's start with this. Imagine an ice cube left out on a table that melts and just turns into a puddle of water like this. So we know that the basic idea is that over time, energy goes from being concentrated to being spread out evenly. So when you have an ice cube that is frozen and is a solid chunk of ice, it's colder than its surroundings. Okay, so on average, its molecules are jiggling around more slowly than its surroundings. But over time, it exchanges energy with its surroundings until on average, everything has the same amount of energy. Okay, if we look at this second example, it's cream being mixed into coffee. Okay, so the idea is before the cream mixes into the coffee, there is a concentration of cream in one part of the coffee and pretty much no cream in other parts of the coffee. But if you stir it around and you just wait for a while, that cream becomes evenly spread out within the coffee. And again, that's just another example of a system reaching thermal equilibrium. And one last thing I'm going to point out about both of these cases is notice how once the system reaches thermal equilibrium, it doesn't go back, right? So in other words, the ice cube, once it melts, it's not like that water is going to freeze again and form another ice cube. And when you mix the cream into the coffee, it's never going to unmix itself and separate. It's a one-way street once you reach thermal equilibrium. Okay, so the next thing we'll talk about here is heat capacity, specific heat, and latent heat. So let's start with heat capacity. So the idea here is when you have energy flowing into a system, we know that its temperature is going to increase, right? Of course, if a system gains energy, its temperature will tend to increase. And on the other hand, when energy flows out of a system, its temperature is going to tend to decrease. Now, there's one little caveat to this. We're assuming there's no phase change happening. So in other words, nothing is melting or freezing or boiling, just no change in phase. But as long as that's the case, if we have a positive Q, that means energy is flowing in, then we have a positive delta T, a temperature is increasing. If we have a negative Q, again, that means energy is flowing out, that implies that the temperature is decreasing, okay? So that's pretty straightforward to understand conceptually. So typically what we're gonna see, this is an experimental result, by the way. Typically what we're gonna see is that there's a linear relationship between heat and temperature change. In other words, there's a really simple relationship between Q and delta T. They're just linearly proportional to one another. So if we want to put that in an equation to say that Q is just directly proportional to delta T, we'd say Q is equal to C times delta T. And this capital C, for our purposes, is just some kind of constant of proportionality in the equation to make it work. So we'll call that constant, that capital C, the heat capacity of the system. And if we kind of think about what it means, the heat capacity of a system is just the amount of energy that you would need to put into the system to change its temperature by a certain amount. Okay, so if we're using the Celsius scale, we would say by 1 degree Celsius or 1 Kelvin. Okay, so the SI units for heat capacity would be joules per Kelvin or joules per degree Celsius. Okay, so the heat capacity tells you how much energy you need to put into the system to get the temperature to change by 1 degree Celsius or 1 Kelvin. Okay, next, let's talk about specific heat. And this is what we're going to use much more often than heat capacity, by the way. So heat capacity, capital C, that's what we just defined. If you think about it, it's going to depend on the size of the system. So let's say we have, 2 kilograms of ice. Well, that's going to have double the heat capacity of 1 kilogram of ice because, of course, the bigger the system is, the harder it's going to be to change the temperature, the more energy you're going to need to change the temperature. So that's why we define something called specific heat, which is lowercase c. And specific heat does not depend on the size of the system. It only depends on what the system is made out of, what the material or what the substance is that the system is made out of. So mass-specific heat, the definition of this is the amount of energy required to change the temperature of 1 kilogram of the substance by 1 degree Celsius. So, okay, lowercase c, specific heat, uppercase C, heat capacity. How do you go from one to the other? Well, you simply just divide the mass out. So if I want lowercase c, I take uppercase C and divide the mass. And that way, the result is independent of what the mass is. Okay, so we saw before that Q is equal to uppercase C times delta T. Well, uppercase C is equal to lowercase c times m if you just take the definition I gave. So therefore, Q is equal to m times lowercase c times delta T. In other words, that's the same exact equation as before. Now we're using specific heat instead of heat capacity. Okay, so let's really break this down. Q, that's on the left side of the equation, is the heat that's either flowing into or out of the system. So if Q is positive, the heat's flowing into the system and increasing the energy. And if Q is negative, the heat's flowing out and decreasing the energy. Okay, M, that's just the mass of whatever system you're looking at. Lowercase c is what we just defined. It's called the mass-specific heat of the system. And it depends on the material or the substance your system is made out of. And then finally, delta T is the corresponding temperature change that happens. Okay? So the last thing we'll do here is talk about the units. The SI units for specific heat are going to be joules per Kelvin per kilogram, or you could say joules per degree Celsius per kilogram. Those are the units that we'll have. And if you think about the units, it's the same units as for heat capacity, but since we're dividing out the mass, now we have kilograms in the denominator. All right. So the next thing I want to talk to you about is a famous experiment done by James Joule to measure the specific heat of water for the first time. And you probably recognize the name James Joule because our SI unit of energy that we use in physics is a joule. And of course, that was named after him. So a little bit about James Joule. He was a physicist, of course, and he studied thermodynamics and did a lot of important work in thermodynamics. But a fun fact about him is he was also a brewer. He liked to brew beer. And in fact, that was his day job, I believe. So anyway, let's talk about the experiment he did. So the apparatus, the experimental setup, is shown in the diagram on the right. And so what you see is we have hanging weights that are connected to a pulley by a string, and that string is wrapped around a shaft, which can turn. So if you follow that shaft down, there are little paddles that can also turn, and those paddles are inside a big bucket of water, okay? So here's how you do the experiment. you start those hanging weights off at rest, some known height above the ground. And then you let the weights go. So here's what happens when the weights start to fall to the ground. Well, they're going to start to turn that little crank and turn the paddles in the water. And those paddles are going to stir up the water. And of course, that's going to heat the water up, right? Now, the paddles eventually come to a stop because of the drag forces within the water. So if you wait long enough, basically everything stops moving, okay? So the weights hit the ground, the paddles stop turning, and everything stops moving. But the temperature of the water is going to increase as a result. See, the thing is, because you knew the mass of those hanging weights and how high above the ground they started off, you know exactly how much energy was put into the water. And if you have a thermometer, you can also determine how much the temperature of the water increased, which is exactly what we want to do. We want to know how much energy do you need to put into the water to get the temperature to increase by a certain amount, right? That's how we measure the specific heat. And so that's exactly what James Joule did. And the result of this experiment is he consistently found that the amount of energy that's going to be required to raise the temperature of 1 kilogram of water by 1 degree Celsius is 4,186 joules. So what we say is the specific heat of liquid water is 4,186 joules per kilogram per degree Celsius. Okay? So here's a question for the class. Try to work this one out. How much energy is given off when 45 grams of liquid water cools down from 65 degrees Celsius to 25 degrees Celsius? So try to see if you can calculate this, and then we'll go through it. So here's the idea. We know that Q is equal to mc delta T. So Q is the amount of heat flowing in or out of the system. M is the mass. Lowercase c is the specific heat. And then delta T is the temperature change. So in fact, we can just directly calculate Q because we know the mass is 45 grams. So 45 times 10 to the minus 3 kilograms, if we want to put it in SI units. Specific heat is 4,186. We have joules, and then kilograms to the minus 1, and degrees Celsius to the minus 1. And then we have our temperature change, which in this case, our final temperature is 25 degrees Celsius, and our initial is 65 degrees Celsius. So that's here, T final minus T initial. That's what we mean by delta T. So you can calculate this directly, and if you notice, all the units cancel, kilograms, degrees Celsius, but the units of joules remain. So this ends up coming out in joules. We have minus 7,535 joules. Technically, we'd want to keep 2 sig figs on that. So roughly, negative 7,500 joules. The negative sign, by the way, tells you that heat is flowing out of the water. That's what the negative sign tells you. And that makes sense because the temperature is going down. You'd expect a negative value for Q. Okay, so that's how you do that. And that's where we'll end this video. In the next video, we'll conclude the lecture on this basic thermal physics review, and we'll finish it up. So I'll see you in the next video. Until then, take care.